So let's do a second example regarding applications of derivatives. And you may have noticed in my past video and regarding this series, I'm not really worrying about and working on the graph of the chart per se. I'm just worrying about the increase or decrease of the function. Okay, that's what I'm only caring about so far. Okay, eventually we will do an example where we will care and pay attention to the graph of the chart. Okay, but right now it doesn't really concern me. Okay, and this is going to apply for this function as well. Okay, we're only going to find the pattern and the intervals of increase of the function and decrease of the function. Okay, this is the example that we have. F of x equals x over x minus 2. Okay, so again, procedure is the same. We find y prime or f prime of x, and in this case f prime of x is going to be, and let's do it real quick here on the left, and then I'll draw the solution over there. Okay, this is the derivative of a quotient division, so I'm going to have x minus 2 squared at the bottom, and on top I'm going to have x minus 2 times x prime minus x minus 2 prime times x. And this is going to be x minus 2 times 1, which is x minus 2, because the derivative of x is 1, minus derivative of x minus 2 is 1, derivative of x is 1, and derivative of minus 2 is 0, x, okay, over x minus 2 squared. The x's cancel each other, x minus x is 0, and then I have minus 2 over x minus 2 squared. Okay? I found the derivative, now I'm going to write the result here. Minus 2 x minus 2 squared. Let me erase this. Now it's going to be funny because remember in my past video I said now we have to find the problematic points, and you said, well, you know, that's kind of a fuzzy word. And I say, well, I mean, it's funny because I like to call it that way, you know, problematic points, because it includes any single point that means an issue to the function, okay? And it doesn't necessarily have to mean points where f prime is equal 0, but any point where there's an issue in general with the first derivative, okay? So we find problematic points or problem points. Like for instance, f prime of x equals 0. Okay? But in this case, if I was to make f prime equals 0, it would look something like this, right? 0 equals minus 2 x minus 2 squared. Right? And there's no, real way to make this expression 0. So we know that, there isn't a point per se that makes the first derivative 0, but there is a problematic point, and that's why I call them problematic. Okay, they're problem points, they're issue points. Okay, there's points where something is not right in there, and in this case, well, the issue point, it's x equals 2. Why? Well, because if x equals 2, then we're going to have 0 at the bottom part of the division, and we're going to have 2 over 0, and that's infinite, okay? Not quite 0, but we know that there is an issue with the first derivative here, okay? You know that there is something happening on in the function in this particular point. And more importantly, it also happens in the function original point as well, okay? X minus 2 is 0. If x is 2, well, we have an issue right here. We're going to have 2 over 0, okay? Other than that, we don't have any more problem points, okay? There's no other way for this expression to be 0, okay? This is something that never happens, okay? So there are no more points. The only one is x equals 2. And look where it comes from the denominator of the original function, okay? Also shared by the denominator of the f prime. So we have two intervals, okay? Since we have 1 point, we have two intervals. Blue, sorry. So we have two intervals. The first one is minus infinite 2, and the second one is 2 positive infinite. Okay? So again, what we're going to do is pick a random point in each interval, evaluate it in f prime to see the sign of f prime. Okay? We don't really care about the value, only the sign. Okay? So now we evaluate a random value of the intervals of each interval in f prime of x. So let's pick a random value from the interval minus infinite 2. Well, the easiest one would be 0, right? So let's do that. F prime of 0, well, f prime of 0 is going to be 0 minus 2. It's going to be minus 2 squared, which is 4. Minus 2 over 4 is going to be minus 1/2. Doesn't matter the value, what matters is the sign. Negative, okay? Let's pick a random value from the second interval, 2 infinite. Let's do 3, an easy one. If we do f prime of 3, then we're going to have 3 minus 2, 1. 1 squared is 1, and minus 2 over 1 is negative. Interesting. This is right. Let's do it again. Let's do another value from the first interval. Let's do minus 1, okay? Minus 1 minus 2 is minus 3. Minus 3 squared is 9. Minus 2 over 9 is minus 2 nines, okay? Doesn't matter the value, what matters is the sign. It's negative. So this is right, okay? And let's do a second value just to be safe on this interval. Let's do 4. 4 minus 2, 2. 2 squared is 4. Minus 2 over 4, minus 1/2. So it's still negative. Well, what's happening here? Well, as you can see, the sign of this denominator is always going to be positive because we have a square right here. Doesn't matter what number we bring, the sign of this is always going to be positive, okay? You can even do it right here. In f prime, the sign of the lower part is always going to be positive. Doesn't matter what we put because we have a square. And a number, when it's squared, is always going to be positive. In the upper part, we have minus 2, which is a constant. It's not affected by the variable x. Okay, there's no x in there. There's no variable. There's nothing going on. So the sign of the upper part is always going to be negative. Therefore, f prime is always going to have this sign, minus over plus. And minus over plus is minus. So that means that the sign of f prime is always going to be negative. F prime is negative for all x in real, except of course x minus 2, x equals 2. But other than that, f prime is going to be always negative. So in these two intervals, the function decreases and the function decreases. Well, you will ask, well, how's that possible? Can a function be decreasing always? Even if we have two intervals that are delimited by a problematic point? Well, yes, of course. Do you remember the graph of tangent and cotangent? Let's do it real quick, okay? Let me erase here. And of course, there's more easier examples than tangent and cotangent, but I want to show you something, okay? If I was to graph tangent, the graph would look a little bit like this, you know? And you can see this in the video of trigonometric functions. All right? This is x, and this is y. If I was to graph tangent, it looks like this. It's a function that is always, always increasing. It's always, always increasing because I read it from left to right and from down to up. It's always going north. Okay, this is tangent of x. Cotangent, if I was to graph cotangent, well, it's going to be the same thing but opposite. It's going to look like this. If this is y and this is x, if I was to graph cotangent, cotangent is going to look like this. Whoops, sorry, made a mistake here. I mean, not exactly like this, but you know, you pretty much get the sense. So this is a graph that is always decreasing. It has a problematic point right here, periodically, as you may have remembered, but it doesn't matter. Other than that, it's always decreasing. So in this particular example, where we only have a problematic point that is x equals 2, we can say that, for instance, 2 is right here. Okay, this is the only problematic point. However, the function, regardless of it, it's still decreasing forever and ever and ever. Okay, that is the solution for this example. Okay, this is a function that is always, always decreasing. It has a problematic point, but it doesn't affect the increase or the decrease of the function. Okay, hope you learned a lot about it. Keep in mind this doesn't matter the value. Only thing that matters is the sign. Keep in mind this: if I have a constant, the sign is always going to be the same. And if I have a square, the sign is always going to be positive. So minus over plus is minus. So that means that f prime sign is always negative for all x, except of course for a problematic point. Okay? Next video, next example.